All right, this section is about continuity, which really is self-explanatory. A function f of x is continuous at a point a if and only if the following three conditions are satisfied. So the first thing is f of a is defined. So in other words, if you have a number, let's say f of 3, and it has to be defined, and we'll look at what that means here. The limit of f of x as x approaches a must exist. So the function has to be defined at that point. The limit has to exist at that point. And then the limit of f of x as x approaches a has to equal the function value at a. And if that's true, then we have satisfied the definition of continuity. A function is continuous at a point a if it fails to be continuous at a, which should be intuitive. Okay, so definition of continuity. So here we're looking. The first one, the first definition, or the first part of our definition, fails because f of a, if there's a hole there, it's not defined. Okay, here, okay, f of a is defined because it's whatever that value is. However, the limit doesn't exist. Okay, here's the third way it fails. The function value exists, whatever this would be. The limit exists, but the two of those are not equal. So that's the part 3 of the definition fails. All three of these have to be true in order for a function to be continuous or to satisfy the definition of continuity. So let's look at an example. Using the definition, determine whether the function is continuous at x equals 3. And here's what we're looking for. These three have to all be satisfied. So let's look. And so what we've done, we've graphed. Here's negative x squared plus 4. Here is 4x minus 8. Okay. And when x is less than 3, of course, we're looking at this function. When x is greater than 3, we're using the second function. So let's look at the limit as x approaches 3 from the left, okay, because that's where we're coming from the left, would be in the top function. What is the limit there? And it looks like it is about negative 5 if we come over. We could also plug our 3 in, because 3 squared would be negative 9. Negative 9 plus 4 is negative 5. So we can figure that out without the graph, but the graph is sure nice to have. And we can do the same thing coming from the right. We're going to use the second function. Plug 3 in. We get 4 times 3 is 12. 12 minus 8 equals 4. So right now, the limits do not exist, so it is not continuous. So this fails right here. Sorry. It's not continuous at the limits don't exist, and also the function value are not equal to the limit. So technically, it looks like 2 fails and 3 fails, but 2 fails right here because the limit has to exist and it doesn't. There. All right. Continuity of polynomials and rational functions. Polynomials and rational functions are continuous at every point in their domains. Previously, we showed that if p of x and q of x are polynomials, then the limit of p of x as x approaches a, you just substitute a in for every polynomial p of x. And then if we're looking at a rational function, you can do the same thing, p of x over q of x, p of a over q of a. Okay, and again, if q of x does not equal 0. Therefore, polynomials and rational functions are continuous on their domains. So let's look at an example. Determine the points, if any, at which the function is discontinuous. Infinite discontinuity at x equals ln 2. So what are we talking about here? Let's look at our function. Okay, here's our function, f of x 5 over e dx minus 2. Well, if we set this equal to 0, because that's what we're looking for, that we need to know where in the denominator would that equal 0. Well, that would be e to the x power equals 2, and we take the ln of both sides, which give us x equals ln 2. So that would be a discontinuity where x equals ln 2. Okay, what about the next example? And again, we would look at the denominator. What would give us 0 in the denominator? So we would set square root of x equal to 0. And so where x equals 0 would be what would be an issue. Could be anything else but 0. Okay, the function is defined for all x's in the interval 0. It has to be greater than 0 as well, because we are dealing with an even root. So x has to be greater than 0. So it would be 0 and anything greater than it. So 0 to infinity. Now let's look at the types of discontinuity. And you can have a removable discontinuity. And here's kind of the definition of a removable discontinuity. The limit may exist. However, the function value at that would be undefined. So when we state the limit f of x as x approaches a exists, we mean that the limit of f of x as x approaches a equals L, or a real number. Okay. You can have a jump discontinuity. Now that's where our limits would not equal each other, so the limit would not exist here. And the note states that that the limit of f of x as x approaches a from the left, and the limit of f of x as x approaches a from the right both exist. We mean that both are real valued numbers, so they have to be real numbers. And neither can take on the values of positive or negative infinity. So remember what a jump discontinuity, or we're going to look at what those look like here. And then we also have infinite discontinuities, and that's where we're looking at infinity, if our limits are going to infinity. And just remember, infinity is not a real number. Okay, so here's what we're looking at as our different types of discontinuities. Here we have a removable discontinuity, so you can see the limit exists, but the function value does not equal the limit. Here we have just a jump discontinuity where the limits do not exist. Okay, and then here's an infinite discontinuity here. All right, so let's look at our function that we have up here. So plug the 2 in to start with, and you notice we'll get 0 over 0, so we can factor the numerator. That cancels this x minus 2, and so we would end up with a limit equal 4. But think about f of 2 is not defined, right? Because x can't equal 2. So that would be, we can define it and remove the discontinuity. So that's where we get that removable discontinuity, because they actually go away there. The limit does exist. However, the function value there is not equal to that limit value. So we do have a removable discontinuity. Let's look at let's look at a different one here. Here we have a function, x over x squared minus x. It has a removable discontinuity at x equals 0. Infinite discontinuity at x equals 1. Okay, because think about what happens when x equals 0. So if we right away, we need to know what will give us 0 in the denominator. And we can figure that out here by setting this equal to 0. Then I can factor the bottom, and what happens to that x? So here's where the x equals 0, and here's where the x minus 1, or the x equals 1 comes from. So I put 1 in here, it ends up being undefined, and then if this is 0. But this one's removable, so that's why the one at x equals 0 is a removable discontinuity. Okay, it's a hole there. And then the other one is a vertical asymptote there. It doesn't go away for us. It's still there. So that's going to be an infinite discontinuity. Okay. Continuity over intervals. A function of f of x is said to be continuous from the right at a if the limit from the right equals the function value at a. And then the same thing can be said from the left. It's continuous if the limit of the left-sided limit equals the function value at a as well. So an example, as we can look here, if we're looking at our function here, we want to know where is there a problem with it. And anytime you have variables in the denominator, you always want to see if there's an issue with it. And here it would be, it looks like at 0, because if we factor an x out, we would have x times x plus 2, and at negative 2. So that's places where there's going to be discontinuity. It's continuous over the other intervals, except at 0 and at negative 2. So a function is continuous over an open interval if it is continuous at every point in the interval. A function f of x is continuous over a closed interval of the form, and you can see the bracket a, b, if it is continuous at every point in a, b, and continuous from the left, from the right at a, and is continuous from the left at a. Continuity over other types of intervals, such as if they're half open, half closed, are defined in a similar fashion. So if we're looking at intervals, we have open intervals, we have closed intervals, and then we have some that are half open, half closed intervals as well. So continuity over interval, let's decide here whether it is continuous on this interval, and it helps. Of course, graphing is very helpful. Decide if this is continuous at where theta equals pi. If it's discontinuous, what type of discontinuity is it? Okay, so let's look. It is an infinite discontinuity at theta equals pi. Tangent theta, as tangent is going to 0, where as theta is going to pi. So the limit of the function as theta approaches pi does not exist. And right here is pi, and we can definitely see that we have an infinite discontinuity here for this particular function. Okay. What about this function? Well, we know it's discontinuous at x equals 1, okay, because x minus 1, if x is 1, we get 0 in the denominator. Now we need to just figure out what kind of discontinuity is it. And if you factor the top, you notice these go away, so it's a removable discontinuity where x equals 1. Or as the limit approaches 1 of the function, it's approaching negative 1. But we can see that there's a hole there. So it's a removable discontinuity. Composite function theorem. If we're looking at if f of x is continuous at L, and the limit of g of x as x approaches a equals L, then we're looking at a composition function. Remember, that's a function in a function. Then we know if we have that, then we have f of L. Okay, so what does that look like? And again, let's look at an example here. If we evaluate our limit of cosine x minus pi over 2 as x approaches pi over 2, it's a composite function. We have a function inside another function. So we can find the limit of x minus pi over 2, well, pi over 2 over pi over 2 is 0. So the limit of cosine of x minus pi over 2 as x approaches pi over 2 is the cosine of that limit. Well, we figured out that was 0. So the cosine of 0 is 1. And so that is working with a composite function.